The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
So I'm next. And I will talk to you about some results from a project I've been dealing with for a few years. And what I've done is to characterize the fresh property responses of 3 different types of SCC, those based on powders, VMA, or a combination of those. And of course my focus has also been to see the variation depending on varying aggregate moisture. This is the outline. I will also present some different parameters who influence the SCC fresh properties, talk about the materials I use, the test method, and the evaluation methods. Go into the mixture design, the results, and some correlations, and of course conclusions. So this is how it looks in reality. The concept of robustness, or in this case, lack of robustness. This is from a Swedish project or a construction project. There is as many as 121 batches, and you see the slump flow on the vertical axis here. And this is, I can tell you, if you don't know that, this is a pure nightmare for any contractor, because he certainly doesn't want this variation, because this completely destroys any logistics and planning. So this is how lack of robustness looks in practice. Because if you want this is your dream concrete. This is perfect. This is exactly how underestimating aggregate moisture could look. Total segregation. And in the other end, too stiff. So, like the other guys here, I tested some different parameters and how they influence the rheology response. In this case, I focus on the yield stress, which is correlating very, very much with the slump flow. Increasing yield stress means a decreasing slump flow. And I tested moisture variation of the fine sand content, that is below the 125 microns, and then the temperature in centigrades. So of course the 0 here on the axis means the correct moisture, no error. 20 degrees and 7% sand passing this sieve. And we can see the influence on the yield stress from temperature variation plus minus 10 degrees. Fine sand plus minus 7, meaning that if you go down to from 7 in this direction, that means you have no fines left. And here you have 14%. But to nobody's surprise, sand moisture is of course resulting in a completely different response in terms of yield stress. We did this initially, and of course from that on we focused only on the varying aggregate moisture. So in this project, I used the Swedish cement, and all the concretes are made for housing. They are not civil engineering or infrastructural kind of concretes. So the cement is a SEM2 with approximately 13% interground limestone. Aggregate, and we used to split sand and coarse aggregate at 8 millimeters, so we have those two fractions, and they are of glacial-fluvial origin, granite. Two different limestone fillers, and they differ in fines. You have the medium particle size 40 and 25 microns respectively. Of course, a lot of chemical admixtures, 3 different superplasticizers, and they are all PCE. And I can tell you I had to squeeze really hard to get any other information out of the admixture company. But doing that, yes, these two are configured to enhance stability too. So my question mark here is VMA. Some kind of VMA or polymer configuration. I don't know. 4 different viscosity modifying admixtures. I rather not say enhancing because, believe me or not, they do not increase viscosity of the mix, all of them. Modified starch, microbial anionic polysaccharide, high molecular weight ionic polymers, could be anything, and a polysaccharide. And the response is, of course, slump flow. That's the target. That's always, we control all the mixes in terms of reaching a certain target in slump flow. But also rheology with the Con Tec 4 viscometer, by the way, invented by the next speaker, Olaf Wallevik. And with this one, we measure the Bingham parameters, the plastic viscosity and the yield stress. But also, by slowly rotating the outer cylinder, we can capture the static yield stress. And this is, of course, how the static yield stress increase with time at rest is the structural build-up. We also use the filling capacity, which is this box with a lot of horizontal bars. To skip the details, you can say that from this, because it's transparent, from this area, you actually measure how many percent of this area will be filled up with concrete. So the result is percent. And of course, the self-leveling concrete will be here at 100%. And to evaluation methods then, yes, I had another approach, and you can do this in so many ways, but I used areas. It's the extreme values of the response, in this case of slump flow, times the span in aggregate variation. And I also use plus minus 1% of sand moisture. And you can see that, of course, you can differ between 2 mixes. Quite easy. But you can do the same thing with the dynamic yield stress area to see the difference between 2 mixes. But for these concretes I have tested, I can tell you that there are so good correlation between, like in this case, slump flow and yield stress, and of course it should be. So we don't have to, at least in this presentation, go into characterizing both these parameters because they correlate very well. And also slump flow and filling capacity. And if you have a mix that doesn't block in the filling capacity box, if it flows without any hinder from the bars, this is also in theory what you could expect, because the yield stress or slump flow of the material will only, depending on the yield stress, will just cause different slopes in the box. So this, besides saying that there's a good correlation, it also tells me there is no blocking really involved here. And why should it? Because it's housing concrete. It's not supposed to. So I would like to focus a little bit more on rheology. I don't know if you're so familiar with the concept of rheology, so I will offer you just what it is. Because when you do test slump flow, and if you want to characterize the T50 value, because I think you do very often, and some contractors actually specify both the slump flow and the T50 value. So this is the time it takes to reach, because this concrete is going to spread further. But at this point, that's when you measure the time. And this is very much correlating to viscosity. Because a higher viscosity will take longer time, and vice versa. Like we have heard before, and I showed you the slide just before too, there's a very good correlation between the spread, the slump flow, and the other rheological parameter, yield stress. So this is the Bingham model again, and if you keep this in mind, that this is actually representing what you can capture with the T50 value. And believe me, there's no strict correlations, but they do somehow very much correlate. And slump flow. We go into the concept of rheology area instead, and I still keep putting this for you to remember, because I think that the total spread of the rheology is, in this concept, more interesting than the individual parameters. Because you can have a concrete reacting like this on plus minus 10 liters or plus minus 1% aggregate moisture in yield stress and plastic viscosity. It's huge. And another one looks like this. So the areas, of course, is like this. If you are in particular interested in any of the parameters, you should, of course, skip this and go to see the variation in viscosity or whatever. It might be more interesting for any specific application. Now I show you all the methods and how to evaluate. So this is the two types of reference mixes. And you see the water-cement ratio is kind of high. One of the references is at 0.7, the other 0.5. And for the higher water-cement ratio, of course, I reduce the coarse aggregate in favor for the fine. Here I used the same superplasticizer, but for each category of reference, I changed between the two limestone fillers. Of course, there's different in amount of powders too. You need more powders for the higher water-cement ratio. So there are 4 different reference mixtures. And here are the slump flow responses for these mixes. And the sand moisture deviates here plus minus 1%, and this is the slump flow. And we can easily see that for one of the limestone fillers, we can see much better robustness than for the finer limestone, which is the green and the yellow. If we plot the slump flow area versus the yield stress area, which of course, as I've told you already, those two parameters do correlate, we find quite a linear relation, and we can, from this, identify the least robust mix. And it happens to be at the lowest water-cement ratio with the finest filler. That means lower water from the beginning, and a filler that actually binds more water. On the other extreme, you have the coarser filler and the higher water-cement ratio. But this is knocking in open doors, because we have already heard this. The lower the water-cement ratio, the less robust. So using this reference mix, this is the one, I designed 3 sets of different SCC types. Powders with, as the reference had, 100 kilos of limestone, 40% 8 to 16 millimeter aggregate. I tested 3 different plasticizer types and also 3 different VMI types, 1, 2, and 3. And exactly like Kamal said, this is very low dosages. For the combination, I reduced the limestone filler. I had to reduce a little bit the coarse aggregate in favor for the fine. I included here another VMA, but here we have the VMA dosages just according to the producer's recommendations for stability. And since I'm sorry to say that, you cannot just add VMA to any mix and think that you can get an SCC, because you see, if I take away all the powders, the consequence is I had to go further down in coarse aggregate to increase the sand, the fines of the sand. There's no way VMA can just stabilize this, just like that. Well, I cannot be categorical. I mean, I have tested a few of the VMAs. There might be VMAs who do the trick out there. There are probably, what you say, Olaf, some 50, 60 different VMAs on the market. Yes. So going into the results, now you know what the rheology area represents. So you can evaluate that, of course, higher the bar, the less robust the mix. And here we have the 4 reference mixes. Again, this is the reference I choose for all the others. And I compare the other bars here with this level. And to my surprise, just changing the super plasticizer type 2 and 3 with a stabilizer or whatever stabilizing configuration, whatever it is, I can increase the robustness quite considerably. We also see a VMA of type 1 who actually cannot perform whatsoever in either of the 3 different powder combination of VMA type of SCC. But we have others that works better. But you see, if we disregard this VMA 1, we can basically see that small dosages of some kind of VMAs can actually enhance robustness quite considerably. And it's not really easy to do it with only VMA. Because what we don't see here is also a difference in paste volume. And to increase the paste volume is also a way of increasing the robustness. So going to only VMA, we have less paste volume too. So there, like always when you do comparison of different concrete mixes, you cannot just vary one parameter. There's always something else varying with it. But since I'm also very interested in formwork pressure, structural buildup is of course also of interest. I didn't show you, but I mean the structural buildup area is just the same way as I did the others. An area with extreme values of structural buildup. And that's Pascal per second. And you can see again that for some mixes you have huge variation. And this concrete was so stiff on the side with less water, so I didn't want to risk the rheometer, really. It was so stiff that you can burn the motors. But this is not very encouraging, is it? When you have prediction models based on this parameter structural buildup to predict formwork pressure, robustness in terms of structural buildup becomes a little bit more interesting then. So you really want a reliable mix also here. And I think I can identify the powder SCC with VMA 3 performing really well again. I'm not going into details about the products here, but my message is to just test. Just don't go out of your normal box, because there are plasticizers and VMAs that actually could enhance robustness quite a lot. And then another few correlations which is quite interesting, and I think Kamal has reported on this before. I mean, the structural build-up correlates with just a single measurement of the static yield stress at rest. Is this value correlating to the slope? 0.88 is fairly good. But if you go to the structural index, it's much, much better. That means that this one correlates to the product of these two. This is just for curiosity anyway. Has nothing to do with robustness. So, my conclusions. The more free water, higher water cement ratio, coarser powder, depends, what I mean is the powder, is it water demanding or not? But the more free available water for the mix, the more robust the SCC becomes. And the type of plasticizer is important. You can probably test a few ones and see different results. While except for the SCC with VMA 1, which didn't perform well in any sense, the powder type of SCC is generally more robust. But there are others working also. Yes, in this case, for the powder, VMA 3 performed best in so many ways. And there are some strong correlations which are maybe they should be. Theoretically they should be. But I'm happy I got them anyway, because if you get a scatter when you need a good correlation, you're in deep water, aren't you? Thank you so much.